Hello and welcome to Study Room. Thank you so much for giving us the opportunity of being your study partner. In this lesson, we'll be learning about Chapter 3 of Grade 9 Chemistry, that is atoms and molecules. In the previous chapter, we had learned about whether matter, they are pure substances or whether they are mixtures. We had learned about the different ways of segregating the components from a mixture. We had learned about the physical and chemical changes. All in all, in the previous two chapters, we had learned about the macro properties, looking at matter from the macro scale, right? In this chapter, we'll be delving deep into the microstructure of matter. We'll be looking at the atoms and molecules, the small components of matter, what matter is essentially made up of, and we'll be learning how to represent them, and we'll be learning the different ways how we represent matter in terms of atoms, molecules, their chemical formula, so on and so forth. So let's get started with the chapter. History of atom. An Indian philosopher, Maharishi Kannad, around 500 BC, postulated that if we go on dividing matter, which in Hindi we also call padarth, we shall get smaller and smaller particles. Ultimately, a stage will come when we shall come across the smallest particles beyond which further division will not be possible. And he named these particles Parmanu. So basically, what he's saying is that matter, what we see in front of us, they are very hefty, lofty, and very concrete structure of made up of particles. We know that matter is made up of particles, right? But if we were to determine the essential qualities of these particles, if we were to determine the structure of these particles, how these particles react with each other at the structural level, right, at the very minutest level possible, all right, and those minute level may not be even visible to a naked eye. So if we this Indian philosopher, he postulated that if we were to divide matter into smaller and smaller particles, we would be ultimately reaching a stage where further division will not be possible, and these particles we will name them as Parmanu. Moving on to the history, another Indian philosopher, Pakuda Katyayama, elaborated the doctrine of the previous said philosopher, that these particles normally exist in a combined form, which gives us various forms of matter. So what this philosopher added on to the previous one was that yes, matter can be divided into smaller and smaller particles known as Parmanu, but they do not exist in that stage. They react with the atoms and molecules. They react with that smallest part of other elements, of other compounds, and they exist in nature in this combined form. And that is how we perceive matter. All right. Around the same era, ancient Greek philosophers such as Democritus and Leucippus suggested that if we go on dividing matter, a stage will come when particles obtained cannot be divided further. So the similar thing that Indian philosopher had postulated. Democritus called these invisible particles atoms, atoms meaning indivisible. So basically what that Indian philosopher called Parmanu, this Greek philosopher Democritus, he is calling them atoms. And why is he calling them atoms? He's calling them atoms because these particles, they won't be divisible in any other matter, in any other way. So for example, you use a pencil, and the name of the pencil, it also has a lot of atoms. It also has a lot of minute particles that they stack upon each other and give this concrete structure of the name of the pencil that you use, that is the graphite, that is carbon. Okay, so what this picture is designating is that this graphite is made up of tiny atoms, such as the structure over here, and there must be millions and billions of these atoms stacked upon each other that give this whole cohesive visual perception. All right, we will be now learning about the laws of chemical combination. Now that we know that some philosopher, they talked about how matter is divisible into further components, and we reach a stage where no more division is possible, right? So these small minute particles, they must combine with each other to exist in a stable manner so that we may use them, or so that that is how they exist in nature. And the ways in which they combine with each other, there are some laws to that. So let's look at them. Establishment of these laws. So Antoine and Lavoisier, a French philosopher, laid the foundation of chemical sciences by establishing two important laws of chemical combination. These laws were established after much experimentations by Lavoisier and Joseph L. Proust. So two scientists, they laid out some laws, and these laws were very essential in knowing how two atoms or how two molecules of maybe same elements or different elements, they combine with each other, and how do they exist in nature. The first law that we will be learning is the law of conservation of mass. Law of conservation of mass states that mass can neither be created nor destroyed in a chemical reaction, but can be transformed from one form to another. So what we see here is that the amount of matter that exists in nature of a particular element or for a particular compound, when it reacts with some other element, some other compound, the resultant mass that we get would be the same mass that we had previously. All right, so for example, this is an unlit candle, and when a chemical change happens, when we light this candle and when the wax, it melts, so what we will observe here, that the mass of this candle that we had earlier would be the same amount of mass that we'll get later on, although we may see a very drastic physical change, that is that this tall candle has now shrunk, melted into this small form. But nevertheless, the mass, since it cannot be created nor can it be destroyed, so the mass would be the same. And according to this law of conservation of mass, the mass of product in a chemical reaction must be equal to the mass of the reactant. So if you were to determine whether in a chemical reaction how things are reacting with each other, the most stable and the most fixed point of axis that you can take is the mass of the chemical reactants and the mass of the chemical product that you get after the reaction. The activity to demonstrate this conservation of mass, we take 1.25 gram of copper sulfate and 1.43 gram of sodium carbonate. Okay, then we prepare separately a 5% solution of each in 10 milliliter of water. All right, now we take a little amount of solution of sodium carbonate in a conical flask. So this is the conical flask we have taken, and this here is the solution of sodium carbonate that we have added into the flask. Now this is a small ignition tube. If you may see here, this small test tube. In the small ignition tube, we have hanged it to the flask carefully, and we have added some solution of copper sulfate into this tube. Now we weigh the flask with its contents carefully. Okay, and we also put a cork on the flask so that no amount of air can interfere with this chemical setup. Now tilt and swirl the flask so that both the solutions get mixed and weigh each other again. So what we are doing here is, we have in the conical flask we have taken some solution of sodium bicarbonate, and in the ignition tube we have taken some solution of copper sulfate. All right, we have added a stop cork and we shake and swirl these two solutions together so that a chemical reaction may take place. And we had weighted the setup, we have weighted the mass of the setup before, and then we weight the mass of the setup afterwards. What we observe is a blue cloudy precipitate that is obtained, and it shows that a chemical reaction has taken place. But the mass of the flask that we had taken before this experiment is now equal to the mass of the flask that we obtained after this experiment has been performed. So we can conclude that mass is always conserved. This is the second law that Lavoisier and Proust had postulated. This is the law of constant proportions. Many compounds were composed of two or more elements, and each such compound had the same elements in the same proportions, irrespective of where the compound came from or who prepared it. This led to the law of constant proportions, which is also known as the law of definite proportions. This law was stated by Proust as, in a chemical substance, the elements are always present in definite proportions by mass. So this law postulates that, for example, in water, We know that there are two parts of hydrogen and one parts of water, right? But so what this law is stating that however the however in the form of the water we take, whether be it in the state of liquid, whether it be in the state of ice, that is solid, the solid state, or whether it be in the gaseous state, as in the water vapor, the in that chemical substance, all the atoms and all the molecules of water, they would have two parts of hydrogen and one part of oxygen. This is that constant, that proportion of water, that proportion of hydrogen and oxygen in water is always fixed, it is always constant, and no matter what the state of matter be, this proportion is constant. And this is how we can determine how elements and various compounds, how they exist in in a chemical reaction with each other. Examples to define law of constant proportions. So in a compound such as water, the ratio of mass of hydrogen to the mass of oxygen is always 1:8. Now this ratio is regarding to the mass. So regarding the mass, the ratio is 1:8, 1 being for hydrogen and 2 being for oxygen. Alright. So 1 gram of hydrogen to 8 grams of oxygen, whatever the source of water. Thus, if 9 gram of water is decomposed, we will get 1 gram of hydrogen and 8 gram of oxygen. This is fixed, alright. In ammonia, similarly, nitrogen and hydrogen are always present in the ratio 14:3 by mass. So, we know that hydrogen exists as H2O. So, two very important things that we can demonstrate is that two molecules of hydrogen and one molecule of oxygen, they combine to form one molecule of water. All right, sorry, two atoms of hydrogen and one atom of oxygen, they combine to form one molecule of water. And also to demonstrate the law of constant proportion, and to demonstrate that mass always remains the same, if we are to decompose 9 gram of water, we will obtain 1 gram of hydrogen and 8 grams of oxygen. In ammonia, similarly, the ratio is 14:3 by mass. Dalton's atomic theory. According to Dalton's atomic theory, Dalton being another scientist, all matter, whether an element or a compound or a mixture, they're composed of small particles called atoms. Similar thing what those Greek philosophers and that Indian philosopher had postulated earlier. Maybe different names, but the same postulation. So Dalton's atomic theory provided an explanation for the law of conservation of mass and the law of definite properties. What is the explanation? This can be determined by the postulates of Dalton. So the postulates of this theory may be stated as: all matter is made up of very tiny particles called atoms which participate in chemical reactions. Okay, atoms are indivisible particles which cannot be created or destroyed in a chemical reaction. Now this holds true. Okay, a part of this postulation holds true, but if we look at this first part, indivisible particles. Now I have been telling you till here that atoms are indivisible particles, and this was postulated by Dalton, those Greek philosophers, those Indian philosophers. But the main thing to observe here is that atoms, we know modern science, modern technology, through that we know that atoms can be divided into neutrons, protons, okay, electrons, and so on and so forth, right? But during that time, during the time when these laws were formed, all right, during that time, atoms were considered to be the smallest, the minutest particle that matter can be divided into. Okay, so yes, a part of Dalton's theory, that is untrue, that is false, but some part of it makes sense. Like atoms, they cannot be created or destroyed in a chemical reactions. Some proportions change. Okay, in a chemical reaction, some elements may try to combine with other elements, so the proportions do change, but there is no creation. There is no creation of atoms in a chemical reaction. Atoms of a given element are identical in mass and chemical properties. Atoms of different elements have different masses and chemical properties. Atoms combine in the ratio of small whole numbers to form compounds. Now this is important. This could demonstrate the law of constant proportions that I was telling you about. I was giving you the example of water, like two atoms of hydrogen combined with one atom of oxygen to form one molecule of water. All right. So atoms combine in ratio of number, okay, small whole numbers to form compounds, and the relative number and kinds of atoms are constant in a given compound. So if we are to take a compound of compound, for example, water, the relative number and kinds of atoms, that is H2O, will only be found in that in all the atoms of that water. Question 1. In a reaction, 5.3 gram of sodium carbonate reacted with 6 gram of acetic acid. The products were 2.2 gram of carbon dioxide, 0.9 gram of water, and 8.2 gram of sodium acetate. Show that these observations are in agreement with the law of conservation of mass. Now, what does the law of conservation of mass say? We know that this law states that the mass of the total reactants is equal to the mass of the products obtained after the chemical reaction. So we have sodium carbonate and acetic acid as our reactants, right? So we have 5.3 gram of sodium carbonates, okay, and we have 6 gram of acetic acid. So the total mass of the reactants is 11.3 gram. After the reaction, we get sodium acetate, okay. So we get 8.2 grams of sodium acetate, and we get 2.2 grams of carbon dioxide. I am writing this by looking at this statement over here. And water, we get 0.9 grams of water. So after the reaction, we get 8.2 grams of sodium acetate, we get 2.2 grams of carbon dioxide, and we get 0.9 grams of water. When you add all this, you will be getting 11.3 grams. So after adding the mass of the reactants and after adding the mass of the products, we see that they are equal to each other, and this proves that the law of conservation of mass holds true. Second question, hydrogen and oxygen combine in the ratio of 1:8 by mass to form water. Okay, we are taking the ratio by mass, okay, which means that 1 gram of hydrogen, all right, will combine with 8 grams of oxygen to form water. Okay, what mass of oxygen gas would be required to react completely with 3 gram of hydrogen gas? Okay, we know that 1 gram of hydrogen gas, it has to react with 8 grams of oxygen. Okay, so what amount of oxygen gas, what mass of oxygen gas would be required to react completely with 3 gram of hydrogen? It is simple, right? We simply multiply 3 into 8, okay, we are getting 24 grams. Okay, so when 3 grams of hydrogen reacts with 24 grams of oxygen, then we will be getting the same water molecule. So this is in keeping with mind this 1:8 ratio by mass that designates that there is some constant proportion by which atoms react with each other. When you similarly here, when you try to simplify this ratio 3 by 24, you will again be getting 1 by 8. All right, so this proves the whole constant proportion law. Which postulate of Dalton's atomic theory is the result of the law of conservation of mass? So the result of the law of conservation of mass is the same, that the amount of the mass of the reactants should be equal to the mass of the product. Okay, this is the law of the conservation of mass, and which Dalton's atomic theory proves it. Dalton's atomic theory proves that, you know, in a given element, the amount of atoms that they have, the mass of that particular atom, that will remain constant. All right, so this proves that when a chemical reaction will take place, the conservation of mass would be there. No amount of atoms would be created, no amount of atoms would be destroyed. The number of atoms would be the same, and therefore mass would be the same. Which postulate of Dalton's atomic theory can explain the law of definite proportions? We just saw the law of definite proportions, right? We know that atoms, they combine in the ratio of whole numbers. Okay, they combine in the ratio of whole numbers to give us molecules. So Dalton postulated this, that the ratio of whole numbers is the proportion in which say some molecules of atom combine with some molecules of atom, and this some molecules, they are always represented by whole numbers. Again, the example of water, we have two molecules of hydrogen combining with one molecule of oxygen to give us water. So this is combining in the form of whole, these atoms are combining in the form of whole numbers with each other, and this is how Dalton postulated and explained the law of definite proportion.